Hello everyone, this is Vijetha, Associate Professor in the Department of ECE from MLR Institute of Technology. Today, I would like to talk on AC characteristics from linear and digital integrated circuits. First, why AC characteristics? What are the AC characteristics and what are the frequency compensated techniques or the topics which I would like to discuss in this video. Why AC characteristics? Op-amp is used in, generally an op-amp is used in circuit for amplifying only AC signals. But the first design constraint is to identify whether AC output voltage is small or a large signal. When we are talking with respect to a small AC output signal, frequency response and noise will be the main design constraints. When we are going with the large AC output signals, slew rate characteristics of an op-amp decides whether distortion will be introduced by the op-amp. The gain of op-amp is assumed to be constant for DC and very low frequency of operation. In practice, that the gain is a complex number and as a function of frequency. At a given frequency, the gain A has a certain magnitudes and phase angles. Any change in the operating frequency causes variation in gain and phase angle. Therefore, the frequency response is defined as a manner in which the gain of an op-amp responds to a different frequencies. How the gain is varying with respect to different frequencies. The frequency response plot shows the magnitude of a gain versus the frequency. This is an equivalent circuit of an op-amp. From this circuit, at this point, if you can apply a voltage divide rule, you can write this as V0 is equals to minus JXC divided by R minus JXC into AVID. So, from this equation, you can write V0 is equals to 1 by J omega C divided by R plus J omega C into A0 into VID. This is how you got this expression. V0 is equals to 1 by J omega C divided by R0 plus 1 by J omega C into A0 into VID. Gain is ratio of V0 by Vi. So, V0 by VID can be given as A0 into 1 by J omega C divided by R0 plus J omega C, which you can write as A0 by 1 plus J omega R0 C, where let us assume F1 as 1 by 2 pi RC. You can rewrite this expression as A is equals to A0 into 1 plus J F by F1, where F1 is equals to 1 by 2 pi RC, where A is a closed loop gain and A0 is a open loop gain. The magnitude of open loop gain is given as A0 by root over 1 plus F by F1 whole square, and phase angle is given as minus tan inverse of F by F1. How frequency response will be there between the frequency and the gain? We got the expression as A0 divided by root over 1 plus F by F1 whole square is the gain equation, magnitude of gain equations which we have derived from the equivalent circuit. So, from this equation, these are the following observations we have done. So, the op-amp gain A is approximately 0 Hz to breakdown frequency is at F is equals to F1. At F is equals to F1, A is given as A0 by root 2, 1, F is equals to F1, 1 whole square, 1, so root 2. So, you can get a minus 3 dB breakdown frequency or corner frequency. When F is greater than F1, the frequency rolls down towards a 0. When F is greater than F1, when F is less than F1, the gain tries to maintain a constant values. So, if this is F is less than F1, where it maintains a constant gain, and at F is equals to F1, you can observe a 3 dB down, and at F is greater than F1, it can be seen that it is a minus 20 dB decaying. These are the three points which are observed based on this equation. A is equals to A naught by root over 1 plus F by F1 whole square. And coming to phase angle, at F is equals to 0, the phase angle is 0 at F is equals to 0, and at F is equals to F1, the phase angle is minus 45 degrees lagging, and at infinity frequency, the phase angle is minus 90 degrees. The same thing has been plotted over here with respect to frequency and phase. And the phase angle we got from the equation as minus tan inverse of F by F1. Coming to closed loop frequency response, the op-amp is generally used in a closed loop configuration, but the bandwidth of an op-amp is very small in open loop, which deals with a constant gain till the cutoff frequency, and it produces a decaying after the cutoff frequency. Therefore, a negative feedback can be used to make an op-amp more versatile. So, it uses a resistive feedback network forming a non-inverting amplifier for input V2 is equals to 0 and inverting amplifier for input V1 is equals to 0. Closed loop transfer function. See, by connecting a resistive network to a inverting terminal, this makes an inverting amplifier when V1 is equals to 0 in this circuit. So, this is a closed loop amplifier. We have given V1, V2 both, so differential amplifier, closed loop differential amplifier. When you have making V1 is equals to 0, then this works as an inverting amplifier. So, by placing a resistive network from output to the invert, this makes this circuit is a closed loop frequency response. And the gain of this closed loop frequency response is given as A naught by 1 plus A naught into beta. So, the stability factor can be determined by making the denominator part equals to 0. So, when the denominator part 1 plus A naught beta is equals to 0, the circuit becomes unstable because A beta will be equals to minus 1 and magnitude of A beta is equals to 1. When 1 plus A beta is less than 0, the A naught beta is negative values. There also your circuit is unstable. When we are going with greater than 0, that is 1 plus A beta is greater than 0, there your AV is less than A naught, that is closed loop gain is less than open loop gain, and the system becomes stable. And the transfer function at 3 different frequencies has given as A is equals to A naught omega 1 omega 2 F3 by S plus omega 1 into S plus omega 2 into S plus omega 3, where omega is equals to 2 pi F. When wider bandwidth and limited closed loop gains are required, suitable compensative techniques can be used. There are two compensative networks, external compensative network and internal compensative network. Coming to external compensative network, again you will be having 3 different types of compensation networks, which is dominant pole, pole 0 and Miller effect. Coming to a dominant pole compensator, you can just add a capacitor over the output side so that it makes to work as a dominant pole compensator. So, dominant pole compensator network is shown in the figure here by just adding a RC network in series with an op-amp. It can also be achieved by connecting a capacitor C at a suitable high resistive node with respect to a ground. The uncompensated transfer function is given as A naught into omega 1, omega 2, omega 3 divided by S plus omega 1 into S plus omega 2 into S plus omega 3. So, the compensated transfer function is given as A naught into, this is for 3 cutoff frequencies. So, this is the transfer function for this dominant pole compensator at 3 different frequencies is given as A naught by 1 plus j into F by Fd, where Fd is equals to 1 by 2 pi Rc and into 1 plus j F by F1 into 1 plus j F by F2 into 1 plus j F by F3 is a transfer function given for a dominant pole compensator network. And here also, based on the frequency, how this compensative network has differed with the uncompensated network is shown in the figure. The capacitor C is selected such that the loop gain drops down to 0 with roll-off rate as given by 20 dB. Normally, the breakdown frequency is selected so that the transfer function A dash passes through 0 dB at pole F1 of A. The uncompensated magnitude plots are shown in figure. The main disadvantages of uncompensated network is the bandwidth of an op-amp decreases, reducing drastically from F1 to FD. The advantage is the noise immunity of the system has been improved. The next compensative network is pole 0 or lag compensator. In this method, by adding a series connection of R1 with R2 and C1, this Z1 and Z2 are parallel connecting. That is, the series connection of R2 and C2 is connected parallel with the R1 so that it produces a output with a modified gain. So here V0 can be determined as V2 into Z2 divided by Z1 plus Z2, where Z2 is given as R2 plus 1 by JXC and Z1 is given as R1. If you can substitute, V0 by V2 is given as R2 plus 1 by JXC divided by R1 plus R2 plus 1 by JXC. The main advantage of pole 0 compensator is the bandwidth has been improved here. The next one is Miller effect compensator, where you can use a C1 R1, that is the combination of C1 and R1 behaves as a phase lead network in the feedback loop of an op-amp, and C1 R1 introduces a phase lead to cancel some amount of phase lag in the loop, where C1 and R2 are connected parallel to the feedback. The next one is internal frequency compensator. Generally for an op-amp, IC741 has an internal capacitor of 30 picofarads which tries to reduce in output signals. The internal compensating capacitor causes an open loop gains to roll off at minus 20 dB that ensures a stable characteristics for the circuit. The second operational amplifier characteristic, AC operational amplifier characteristic is slew rate. Slew rate is an important parameter which limits the bandwidth for a large signal, and it indicates how fast its output voltage can change, and it is defined as the maximum rate of change of output voltage for a change of step input voltage. It is usually measured in volts per milliseconds or volts per microseconds. The slew rate of an op-amp is related to its frequency response. The operational amplifier with wide band have a better slew rate. Let us assume the slew rate limiting affects all amplifiers where capacitors on internal loads or a part of external loads has to be charged and discharged as voltage level varies. Slew rate is determined as rate of change of output voltage with respect to step time, that is dVc by dt max. So, let us assume that Vi is the input signal, that is Vi is equals to Vn sin omega t, and produces the output of V0 is equals to Vm sin omega t, where dV0 by dt is given as Vm into cos omega t into omega. Vm is the amplitude. The maximum rate of change of output voltage, that is dV0 by dt is equals to, we got it as omega cos omega t into Vm. This dV0 by dt will be maximum when you got omega V1. That is, you need to make the cos omega t1 as 1. This can be done and you can get dV0 by dt as W into V1. So, slew rate is given as W into Vm, where W is equals to 2 pi f, that is slew rate is equals to 2 pi f into Vm volts per second. If you can write this equation in terms of frequency, you can write F is equals to slew rate by 2 pi into Vm. And if you can write this equation in terms of V, we can write V max is equals to slew rate by 2 pi f. So, here we have discussed two AC characteristics, two AC op-amp characteristics. One is frequency response, other one is slew rate. Frequency response, how the plot will be there between the frequency and the gain, magnitude of gain, and also we determine how the frequency and the phase angle or changes, and what are the different compensator techniques. So there are two different types of compensator techniques. One is internal and one is external. In external also you'll be having three types of compensative networks, which we can add one resistor and capacitor network at the output side, and one resistor and one capacitor with resistance can be used as another compensative network, and one feedback resistance with the capacitor, you can have this as one more compensative network. And internal compensative network, for this a capacitor has been introduced in the internal circuit of an op-amp, which functions as an internal compensative network. And coming to slew rate, here we have defined as a rate of change of output voltage with step input. The maximum rate of change of output voltage with respect to step input voltage is given as slew rate. These are the topics which I have discussed here in this topic. Thank you.